Lab 5. So the purpose of what I tried to do in Lab 5 is figure out if a trampolinist is breaking laws of physics, and the way I tried to do this considers the trampoline as a spring. So all the important concepts from Lab 4 are going to apply here with regards to Newton's second law and the energy principle, and they're all listed out right here. And the results are, although the model can't really predict it accurately, the trampolinist is not breaking physics. So the initial conditions, because the code base for this lab is the same as Lab 4, because the code base from Lab 4 can actually do a pretty good job of explaining it. All of the initial conditions from Lab 4 apply here. It's just that the numbers are very different in some cases. So you have the initial trampolinist position and the initial spring position, because I didn't put the origin of the coordinate grid in tracker at the center of the trampoline. The mass of the trampolinist, about 77 kilograms or about 170 pounds. That's just an estimate on my part from what I saw in the video. The system is the trampolinist, the spring, and the trampoline at Earth. There's no surroundings. Delta T is 1/800. The spring conditions, K of 4,600 is for the entire trampoline. Obviously, if we decompose that down, each spring is going to have its own K. And L0 is 0 in this case because I just considered when the trampoline wasn't moving that L0 was the resting, that 0 was the resting state of the trampoline. So here's the video. Okay, so the code, again, is the same because this can do a decent job of explaining what's going on. The only things I tried to manipulate were the L hat, and I tried, for the sake of accuracy, to make the if-then statement of only when the guy's actually hitting the trampoline, because that would help mitigate the issue of the model considering the spring and the person to be attached when they're really not. So the results of the model are here, and the only two that really matter are the y position versus time and the energy graph. So on the y position versus time, we have some very obvious peaks and troughs, and a discrepancy very consistently where the model thinks he's going to go down when he doesn't. And this is likely where the question arises of, is he breaking physics? He's really not. What the model thinks is going on is that the spring is going to pull him from his peak y position back down, but he's not attached to a spring. And furthermore, what's going on is that when he bounces off the trampoline, he takes a path that bounces him back into the wall. And what he's doing, essentially, is he hits the wall and kicks up and off, which redirects his remaining momentum up into the y direction from the x direction, and that allows him to hang in the air and allows him to get more air time than he otherwise would have. And you can kind of see this in the energy in the delta E line right here, where these tiny little peaks roughly line up to about this part when he's kicking off the wall. And these highs represent basically that he's getting slightly more gravitational potential energy than he otherwise should. So errors, the code thinks the ball and the spring are attached, they're not. The trampoline is assumed as one big spring. It would be more accurate to decompose it into multiple. Multiple assumptions have to be made about the initial conditions as well. So questions. What if the trampolinist bounced straight up and down? If he did that, he would have gone higher into the air just as a baseline, and the model likely would have done a better job of predicting when he goes up and down, but since there's that issue with the model considering them attached, it still would have more extreme variance. And if every individual spring was considered, it would have its own unique L value.